You're listening to DTFHN for May 5th, 2026. I'm your namespace isolated host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people argue about whether abstractions leak or whether they were never watertight to begin with. Today is a day for appreciating the gaps between what systems promise and what they actually deliver. Let's get into it. One commenter put it perfectly. Async seems like an underbaked idea across the board. Regular code was already async. And then they explain how the kernel already abstracts away waiting, how threads already sleep until ready. The deadpan energy of someone watching an entire ecosystem reinvent operating system primitives. Chef's kiss. This reminds me of 1995. Java launches with green threads. The pitch? Lightweight concurrency without kernel overhead. By 2002, they'd ripped it all out and gone back to native threads, because the abstraction leaked in exactly the ways you'd predict. The JVM spent 7 years carrying complexity that existed to solve a problem the OS had already solved. Just not in the way language designers wanted it solved. Now here's Tweedgolf, an embedded Rust shop, pulling back the curtain on what async actually compiles to. A function that adds two numbers to awaits. Generates 360 lines of champera. The non-async version, 23. The state machine carries a panic variant, so that if you catch an unwind and try to pull again, it panics instead of causing undefined behavior. Which is correct, and also absurd. You're paying for poison semantics on a microcontroller with 64 kilobytes of flash. The proposals here are genuinely clever. What if a future in the return state just returns pending forever instead of panicking? You lose the helpful diagnostic, but you drop the panic path entirely. And panic paths are expensive because the compiler can't optimize away side effects it can't prove won't happen. What if the compiler could see that a sub-future is only pulled once and inline it without the full-state machine wrapper? These aren't exotic optimizations. They're the kind of thing you'd expect a mature implementation to have figured out years ago. Another commenter nails it. I really enjoy witnessing a programming language develop in real time. That's the thing about Rust being open. The project goals process, the mere dumps on Godbolt, the blog post itself. This is compiler development happening in public with the community as collaborators. Someone spots bloat on their embedded target, writes it up, submits a project goal, asks for funding. No permission required, no internal roadmap to lobby against. The embedded Rust folks are doing what open development does best. Finding where the abstraction breaks and fixing it upstream instead of routing around it forever. The tools exist. The compiler is theirs to improve. No winard. What does it mean for a tool to be production ready? Is it the feature set, or is it the operator's willingness to fill the gaps the tool deliberately left open? Docker Compose started life as internal tooling at .cloud, a PaaS company wrapping LXC containers. Now it runs backends for thousands of real businesses. And the fascinating thing is what it chose not to be. There's no control plane, no scheduler watching your host, no reconciler reapplying state. You run Docker Compose up and it exits. Done. The architecture is honest about what it is. A declarative file that wires up containers, networks, and volumes on a single node. One YAML file you can read top to bottom and understand completely. That honesty is rare, and it's worth admiring. The failure modes this article catalogs aren't bugs. They're the consequence of a tool that respects its own boundaries. Orphan containers that keep running after you remove them from the file. Disks filling overnight because nobody scheduled a prune. Health checks that detect failures and then do nothing because there's no supervisor to act on them. A latest tag silently pointing somewhere new. Each one is a deliberate architectural decision. Compose handles declaration. You handle operation. Pull this thread further. Docker Compose is open source. The format is documented. The behavior is predictable. When it leaves a gap, you can see the gap, name it, and fill it. With a cron job, a systemd timer, a watchtower sending sense, or an agent like the one the author's company builds. The comments reflect this beautifully. One person runs Podman with systemd, another uses micro8s. Someone else just handles the handful of quirks manually, because they've learned the territory. Everyone's solving it differently because the tool lets them. Compare that to managed platforms where the gaps are hidden behind an API you don't control, when their objective function changes, when the pricing shifts, when features get deprecated, when the acquisition happens. You discover the gaps all at once, with no way to fill them yourself. The engineering craft here is the simplicity itself. A tool that does one thing, documents its limits, and trusts the operator. In 2026, with Kubernetes available for complex orchestration and Docker Compose available for everything else, the real question isn't whether Compose is production ready. It's whether your operational discipline matches the freedom the tool gives you. The architecture is open. The failure modes are visible. The fixes are commands you can run today. That's how infrastructure should work. Legible, controllable, yours. Moving on. The fundamental constraint in any runtime rewrite is not the language. It's the behavioral surface area. Bun has accumulated thousands of implicit contracts with its users. Every edge case and how it handles module resolution. Every timing quirk in its event loop. Every undocumented interaction between its bundler and its package manager. These aren't in the type system. They're in the test suite if you're lucky, and in production code if you're not. A branch exists on the Bun repository with 773,000 lines of Rust added and 151 lines deleted. Claude wrote it. One of the Bun developers stepped into the thread to say the obvious. 300 comments about code that doesn't work. No commitment to shipping any of it. An experiment, not a migration. But let's take the devil's advocate position. Assume the AI-generated rewrite is garbage. Assume it doesn't pass tests, misses edge cases, produces code nobody on the team fully understands. What have you actually lost? A branch costs nothing. The original Zig code base is untouched, and what you've gained is a structural map. A rough translation that shows you where the hard problems live, where Zig's Compton semantics don't map cleanly to Rust's rate system, where the impedance mismatches will bite you if you ever do commit to the port. The interesting historical parallel is Go's runtime rewrite from C in 2015. They built a mechanical translation tool first, produced ugly but correct Go, then cleaned it up by hand. The machine translation wasn't the product. It was the scaffold. The question for Bun is whether 700,000 lines of LLM output can serve the same scaffolding function, or whether the error rate is high enough that you'd spend more time auditing than writing from scratch. Z to Rust is not C to Go. Z's manual memory management and Compline metaprogramming have no direct Rust equivalents. You're not translating syntax. You're translating design philosophy. Every allocation strategy needs rethinking. Every comp time-generated lookup table needs a proc macro or a build script or a completely different approach. The code is on GitHub. The branch is public. Whether it ships or not, the experiment itself is visible, forkable, examinable. That's the part worth noting. Not whether Bun switches languages, but that the exploration happens in the open where anyone can learn from it. Remember that joy first principle? Here's pure joy engineering. Someone built a tool to find empty movie theaters just for you. I've spent enough time staring at capacity planning dashboards to know that a 10% utilization rate on any resource would get someone called into a meeting. If 10% of your servers were handling 0 requests, you'd auto-scale down. If 10% of your delivery trucks went out empty, logistics would have questions. But 10% of AMC's screenings sell literally 0 tickets. And the projector fires up anyway. Rob Walls built a site that surfaces these ghost showings. The implementation is straightforward. Scrape the booking data. Filter for low or 0 occupancy. Present it as a feed. The interesting part isn't the engineering. It's what the data reveals about how theaters price their inventory. Run this forward. You have a perishable good. A seat in a dark room for 2 hours. Once the showtime passes, that inventory evaporates. Airlines figured this out decades ago. Dynamic pricing, last-minute deals, yield management. Hotels figured it out. Ride-sharing figured it out. Movie theaters are still charging the same $14, whether the room is packed or whether you be sitting alone in a 200-seat auditorium burning electricity for an audience of none. One commenter nailed it. This suggests theaters are at least partially incorrectly pricing things, which explains why they're struggling. That's generous framing. What it actually suggests is that the theater industry has refused to treat showtime scheduling as an optimization problem. They're running a fixed grid regardless of demand signals, then wondering why the economics don't work. Now, someone in the comments raises a fair point. Do enough people buy tickets in advance for this data to mean anything? Maybe that Tuesday afternoon showing of a 3-week-old film fills up with walk-ins. Maybe. But 0 pre-sales is still a signal, and signals are what you build systems around. What I love about this project is the sheer simplicity of it. Public booking data, a filter, a web page. No API key required. No reverse engineering. No terms of service gray area. The information was always there. Someone just bothered to make it legible. That's builder culture at its most elegant. You don't need permission to notice a pattern in public data and make it useful. Go find your empty theater, bring a blanket, the projector's running whether you're there or not. That same energy, noticing what's available and just building, pause, is reshaping how we write code itself. In 1991, when Linus Torvalds posted his hobby kernel to a Usenet group, operating system code went from something you licensed for thousands of dollars to something you downloaded for nothing. The immediate reaction from a lot of smart people was that this would devalue programming. If the foundations are free, why would anyone pay for software? What actually happened was the opposite. Free infrastructure created an explosion of new work built on top of it. The value didn't disappear, it migrated upward. Drew Brunig's list of lessons for agentic coding describes the same migration happening again, one layer higher. When AI agents can produce functional code in minutes, the bottleneck moves. And Brunig is precise about where it moves to. Taste, intent, behavioral contracts. The human judgment that no amount of cheap code can substitute for. Follow his core claim all the way to the end. If code is truly cheap, then re-implementation is cheap. If re-implementation is cheap, then you should optimize for the ability to rebuild, not for the perfection of any single build. That means end-to-end tests that verify behavior, not implementation. That means specs kept in sync as living documents, not frozen artifacts. That means the developer's role shifts from producing code to maintaining coherent intent across rapid iterations. This is serious work, and Brunig treats it seriously. His 7th lesson, find the hard stuff, is the crux. Agents eat boilerplate for breakfast. The vibe-coded prototype is trivial now. What remains difficult is exactly what was always difficult. Security, resilience, the systemic architecture that determines whether your software survives contact with real users. The hard problems didn't get easier. They just lost their camouflage. One commenter from India names the human cost plainly. Junior developer hiring has collapsed. The apprenticeship pipeline, the janitor work that taught people how real systems behave, is evaporating. This matters. The talent that Bruning says agents amplify has to come from somewhere, and right now we're watching one of the ladders get pulled up, but the tools themselves are open. Claude Code, Codex, the entire ecosystem of agentic harnesses. These are available to anyone with a terminal. The same dynamic that played out with Linux is playing out now. When the foundation layer becomes universally accessible, the people who were previously locked out of building get to build. A developer in Bangalore and a developer in San Francisco now face the same marginal cost of code, nearly zero. The question Bruning frames, free as in puppies, is the right one. Producing code was never the whole job. Maintaining intent, compounding decisions, exercising judgment. That was always the job. The agents just made it impossible to pretend otherwise. Remember that open hardware ethos we talked about? Someone took it beautifully literal. Story 6, hand-drawn QR codes. 21 by 21 pixels. That's all a version 1 QR code needs. And Seth Larson looked at a 10 by 10 grid sticky note and thought, yeah, I can split those squares in half. I can make this work by hand. There's something deeply satisfying about this. A QR code is at its core a machine-readable encoding. It's designed for printers, for screens, for automated systems. It is explicitly not designed for a human being with a pen and a pad of sticky notes from a stationery store in Minneapolis. And yet, the craft here is worth appreciating. First, you hit the constraint, 17 bytes at the lowest error correction level. Your URL is 23 bytes, so you improvise. You drop the protocol prefix. Go with just the domain. Then a reader points out something beautiful. Capital letters are cheaper in QR encoding. The alphanumeric character set includes colons and slashes. https://sub-mil-I-l-c-e-n.s-in.div. Fits in 17 bytes when you shout it. The encoding scheme rewards you for being loud. He generates the reference pattern with the one line. Echo -n pipe to the QR command, and then picks up a pen, draws the 3 position squares in the corners, starts filling in timing lines. And here's where the engineering elegance of QR codes reveals itself. Even with a mistake in the data bits, even at the lowest error correction setting, the thing scans. Reed-Solomon error correction, designed decades ago, covers for the wobble of a human hand on grid paper. The question nobody asks about QR codes is why they work so well as a folk medium. People engrave them into wooden boards at restaurants. People draw them on whiteboards. One commenter hand-drew a QR code whose payload was an entire typed letter. Tedious for the sender, delightful for the receiver. The spec is open. The encoding algorithm is documented. The Python package that generates a reference image is free software. There is no license fee between you and a functioning machine, readable GLIT. This is what open standards give you, not just interoperability between corporate systems, but interoperability between a human being, a pen, and a camera phone. The entire stack, from encoding math to scanner software, exists in the commons. which means a sticky note becomes a hyperlink. That's elegant engineering meeting open infrastructure, and the result is pure joy. Open tools reward curiosity. So, what happens when an organization has every tool imaginable and still refuses to be curious? There's a phrase buried in this article that I can't stop thinking about. The adoption unit is no longer the organization, and maybe not even the team. It is the loop inside the work. That's the whole diagnosis in one sentence, and almost nobody is acting on it. Here's the analogy that keeps coming back to me. Mycorrhizal networks, underground fungal meshes that connect trees in a forest. One tree figures out it's being attacked by beetles, synthesizes a defense compound, and the network carries that signal to neighboring trees before the beetles arrive. The forest learns, not because any individual tree is brilliant, but because the transport layer exists. Now imagine a forest where every tree independently invents beetle defense, never shares it, and management occasionally asks the trees to present their findings at a quarterly brown bag session. That's Enterprise AI adoption in 2026. The article describes a situation I've watched unfold with the precision of a slow-motion train derailment. Company provisions 2,000 Copilot licenses. A support team quietly automates 40% of recurring tickets because they know where the pain is. A senior engineer delegates root cause analysis to an agent and gets answers in an hour instead of 2 weeks. A product owner prototypes working software instead of Figma mockups. All happening simultaneously. None of it connected. The company's official AI strategy is still a steering committee deck with 3 bullet points and a roadmap that ends in scale. The old change machinery. Communities of practice, champion networks, enablement sessions. These were designed for a world where knowledge moved at document speed. But the interesting AI work shows up inside a code review on Tuesday afternoon. It appears when someone discovers that a particular class of tasks can run in what the article calls a dark factory. Fully automated, no human in the loop, just validation at the edges. By the time that insight reaches the monthly demo meeting, 3 other teams have already solved it differently or not at all. The missing piece isn't adoption, it's the mycorrhizal layer, the transport mechanism that moves a discovery from the individual who stumbled into it to the organizational capability it could become. And here's the comedy. The tools to build that layer are open, available, ready. Shared prompts, documented workflows, open source agent frameworks, version-controlled automation. The infrastructure for organizational learning already exists in the commons. The bottleneck isn't technology, it's that someone has to actually plant the fungal network, and that job doesn't appear on anyone's OKRs. Moving on. Let me make the strongest case for Google here. On-device AI is genuinely better for privacy than cloud inference. Every query that stays on your hardware is a query that never hits a server, never gets logged, never trains a future model. Google could argue they're doing the responsible thing. Moving computation to the edge, reducing their own data collection surface, giving users AI capabilities that work offline. The hardware is already there. The bandwidth cost is a one-time 4 gigabytes. And the features? Scam detection, writing assistance, are objectively useful. If you asked most users whether they prefer their AI assistant to run locally or phone home to Google servers every time they type a sentence, they'd pick local. Google just skipped the asking part. And that's where the argument collapses on its own terms. The engineering here is genuinely impressive. Gemini Nano is a distilled model optimized for edge deployment on consumer hardware. Getting useful inference out of 4 gigabytes of weights on a laptop GPU is a real achievement. Quantization, architecture choices, the whole optimization stack. I admire the craft. What I cannot admire is the deployment architecture, because the deployment architecture is a command and control system wearing the skin of a feature update. Pull this apart through the bootstrapism lens. 2 billion Chrome installations. Google flips a server-side flag and 4 gigabytes appear on your disk. You delete it. It returns. You delete it again. It returns again. The only permanent removal paths are enterprise policy tooling that home users don't have. Hidden flags buried in Chrome : / or uninstalling the browser entirely. This is not putting tools in people's hands. This is bolting tools to people's hands and removing the release mechanism. The environmental math deserves the full technical picture. 4 gigabytes times even a conservative fraction of 2 billion devices. The author estimates 6,000 to 60,000 tons of CO2 equivalent for a single push. That's not a rounding error. That's a unilateral climate decision made by one company's feature flag infrastructure. One commenter nails the architectural failure perfectly. Language model should be an OS service. Exactly right. A shared, user-controlled, updatable runtime that any application can call. Instead, every browser, every Electron app, every vendor ships their own binary blob into your profile directory, like feudal lords each building their own road system. The model weights are open enough to ship, but closed enough that you can't control them. The inference runs on your silicon, but answers to Google's variation server. Local compute, remote control. That's not edge AI. That's occupation. So what does it actually take to make voice AI feel instant, not local but leashed, but genuinely responsive at planetary scale? A commenter named Sean Dubois shows up in the Hacker News thread to say he's grateful OpenAI publicized their use of Peon, the open-source WebRTC library he works on. That's your entry point right there. OpenAI just published a detailed engineering post about how they deliver sub-300 millisecond voice interactions to what they claim is 900 million weekly active users. And the foundational transport layer is an open-source Go library maintained by community contributors. Let's break this down to what actually matters technically. Voice AI has 3 latency budgets that all have to come in under about 300 milliseconds total. There's the network transit. Get an audio from your device to inference. There's the model computation, generating a response. And there's the return trip. OpenAI's architecture uses WebRTC for that first and last mile, which is the correct choice. WebRTC was designed for exactly this. Real-time media with adaptive bitrate, jitter buffering, NAT traversal. The protocol handles the hard networking problems so the application layer can focus on inference. The engineering details they share are genuinely useful. Thin client architecture. Media routers close to users. Keep alive connections to GPU clusters. Standard distributed systems patterns applied well to a genuinely hard problem. But one commenter flags the limitation that mattered. The real-time audio models are still stuck on the 4.0 family. The transport is fast. The infrastructure scales. The model powering it hasn't kept pace with their text models. Fast plumbing to a slower brain. Another commenter points to PeePaCat, an open-source framework for building voice AI pipelines. And this is where the architectural picture gets clear. OpenAI built their stack on Open Protocol. WebRTC. Then close the application layer. Peppacat inverts that. Open Application Framework. Plug in whatever model you want. Deploy wherever you want. The real contribution of this blog post isn't the proprietary infrastructure description. It's the validation that WebRTC plus server-side inference is the right architecture for voice AI. That pattern belongs to everyone. The Pine maintainers, the PK contributors. They're building the commons that makes all of this possible. OpenAI's 900 million users are at the transport layer, standing on open source shoulders. Moving on. What does it mean to become root if root doesn't mean anything? That's the question at the center of CVE 2026. There are 1431, and it's a question with a lineage. In 1979, Bill Joy added croup to Unix, a system call that lies to a process about where the file system starts. It was the first time an operating system said, "I will let you believe you have power you do not actually possess." 47 years later, Linux user namespaces have elevated that same philosophical trick into a full security architecture. The copy-fail exploit is real, and it is nasty. A scatterless bug in the kernel's AFALG crypto subsystem lets an attacker write to read-only pages in the page cache. The public exploit overwrites SR bin SR with a gulfed LF binary. 22 bytes of actual instructions, setud 0, exact for bin stash done. Inside a normal container running as root, that's game over. Full host compromise. But here's where architecture does what policy never could. The author ran this exploit inside a rootless Podman container, the kind deployed on GNOME's GitLab runners, and traced every syscall. The exploit fires, the corrupted page cache loads, the setud call succeeds, the shell opens, you are now UA0. Congratulations, except that UA0 is mapped through the user namespace to UAG 1000 on the host. Your omnipotence is a local fiction. The kernel didn't block the exploit. It made the exploit's success irrelevant. One commenter asks the obvious follow-up. Can't you just rerun the exploit as the unprivileged host user and escalate again? You could, if the host kernel is also vulnerable. Patch your kernels. But the defense in depth here is real. Rootless containers didn't need to know about copy-fail in advance. The containment is structural, not reactive. This is what good security architecture looks like. Not a signature database, not a vendor dashboard, an open-source container runtime, a decades-old kernel abstraction, and a design principle that assumes breach rather than preventing it. The exploit worked perfectly. It just didn't matter. This has been your daily tech feed for Hacker News for May 5th, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voiced by Quen 3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that makes the world a little more legible. We'll see you back here tomorrow.